Hello friends, in today's video we will learn a very new topic which is quantum mechanics. So first of all we will see the background in which this topic quantum mechanics was introduced. So before we move into the basic concepts of quantum mechanics and understanding the new topic in depth, let us learn a new problem, the blackbody radiation that used to trouble physicists of the 20th century in the first half. A blackbody is a body that will absorb all the radiations that is falling on it, and at thermal equilibrium it will continuously emit blackbody radiations. The physics of the blackbody is very interesting to study, and if we study the blackbody radiations deeply, there are plenty of unresolved problems and plenty of areas that could not be explained by the classical theories existing then. So what are usual examples of a blackbody? A sun or a star can be treated as a blackbody because the radiations emitted are very much similar to the blackbody radiations. Or the common stove that we use is a kind of blackbody. So all these systems that are maintained at a constant temperature and hence which will be emitting radiations can be treated like a blackbody. And if we study the radiations emitted from a blackbody, it is very interesting and reveals a lot of interesting aspects. The experimental arrangement to study the blackbody radiation was set up by Lammer and Pringsteen. They tried to analyze the radiations that are emitted from a blackbody. So for that, the radiations from the blackbody were first rendered parallel by a concave mirror, and the radiations coming from the mirror was passed through a prism. The prism will resolve these incoming radiations into a spectrum. That means it will split the radiations depending on its wavelength, and this was again focused by another concave mirror onto a bolometer. This bolometer is connected to a galvanometer, and depending on the energy of each of the wavelength, the galvanometer will show indications. By rotating the prism, the energy corresponding to different wavelengths can be studied. So this was the experimental setup made by Lammer and Pringsteen to study blackbody radiations. And the results obtained by analyzing the blackbody radiations were very interesting. So they tried to plot the energy of the radiations emitted from the blackbody, with the x-axis being the wavelength lambda in nanometers and the y-axis being the energy emitted, which is u lambda or E lambda. So as you can see, there are plenty of curves drawn here corresponding to different temperature. So for any given temperature, for example, suppose you consider the temperature 4500 Kelvin. At 4500 Kelvin, we know E lambda first increases with the wavelength, reaching a maximum value corresponding to a particular wavelength lambda m, and then decreases for longer wavelengths. So if I plot for any particular temperature, I plot along the x-axis lambda and along the y-axis E lambda, then the shape of the curve will be, first the E lambda will increase with lambda, then after that E lambda will decrease with the lambda, temperature being a particular constant, say 4500 Kelvin. And the maximum value of lambda for which energy is maximum is called lambda n. So this is one of the assumptions, one of the results that we get by analyzing blackbody radiation. Now the second result that we get by analyzing the blackbody radiation is that the value of E lambda for any lambda increases as temperature increases. So you can see different curves drawn here, and these correspond to different temperature. So you can see here, as temperature increases from 3500, 4000, 4500 and so on, the curve is shifting up. That means the value of energy E lambda is increasing for any lambda as temperature increases. So if you take any lambda value and look for various energies at different temperature, the energy is consistently increasing with respect to temperature. That is the second result that we get by analyzing this graph. Now you can see the third result that we will get is that the wavelength corresponding to the maximum energy shifts to shorter wavelength side as the temperature increases. So we have already mentioned the term lambda m. Lambda m is the peak value for which energy is maximum. So this is the lambda m at 3500 Kelvin. This is the lambda m for 4000 Kelvin. This is the lambda m for 4500 and so on. So the lambda m is shifting with temperature towards the shorter wavelength side. So I will show you another graph. So clearly you can see these curves are corresponding to different temperature, and you can see clearly the lambda m being shifted to lower wavelengths as temperature increases. From lambda m1 to lambda m2, 3 and 4, the lambda m is consistently decreasing as temperature increases. So lambda m decreases as temperature increases. So there is one law that tries to explain the relation between lambda m and T. It is called Wien's displacement law. And according to Wien's displacement law, lambda m into T is a constant. That is, the wavelength of the most strongly emitted radiation in the continuous spectrum from a full radiator is inversely proportional to the absolute temperature of that body. So as lambda m increases, T decreases. Lambda m is inversely proportional to temperature. So that is the third result that we get by analyzing a blackbody spectrum. And finally, the fourth result that we get by analyzing a blackbody radiation is that the total energy emitted by a blackbody is proportional to 4th power of temperature. How do you calculate the total energy? For one particular temperature, say for example at 3500 Kelvin, the total energy will be the area under that curve. So there are different energies corresponding to different wavelengths. So to calculate the total energy, you need to integrate the energies of each of the wavelength with the corresponding wavelengths. So integral 0 to infinity E lambda d lambda will be your total energy, and this total energy is actually proportional to T raised to 4. This is a law which is called Stefan's law. So that is the fourth result that we get by analyzing a blackbody radiation. We have defined the characteristics of blackbody radiation. We tried to analyze the radiation spectrum, and we got plenty of results from these spectrum, like Wien's displacement law, the Stefan's law, and the other points that we have mentioned. And one more point to mention, we have stated that according to Wien's displacement law, lambda m into T is a constant. This constant is called Wien's constant. Wien's constant, and this constant is given by 2.898 multiplied by 10 raised to minus 3 meter Kelvin. So this is Wien's constant. So these are the major results that we get by analyzing a black body radiation. As you can see, it is a continuous spectrum. There is energy emitted at all wavelengths continuously. But even then, there are special features of this spectrum that could not be explained classically. For example, we will see later, there are some classical theories that try to explain the black body radiation. For example, the Wien's formula or the Rayleigh-Jeans formula, as will be explained later, tries to explain the black body radiation based on classical theories. But they could not make a complete picture about the black body radiation based on classical theory. Hence, it was necessary to formulate a new theory to explain the black body radiation. So there starts the beginning of the new approach to study microscopic particles and smaller phenomena. So there begins a new branch of physics called quantum mechanics. First of all, we will discuss in the next class how Planck, the scientist Planck, based on quantum principles, introduced and analyzed black body radiation. So as of now, I hope the basic physics of black body radiation is clear for you. Thank you.